Yeah, hello, welcome to this session. I'm not quite sure whether we should start right away or wait for 2 minutes. Okay, I guess I have been informed by the assistant that we should start right now. So welcome to this session B1 of ICALP 2020. I'm the moderator. My name is Thomas Sauerwald, and I will be leading the discussion and the Q&As on 6 papers. I think we will go through them in the specified order from 1 to 6, and each speaker starts with a 2 to 3 minute summary of the main results and open questions, and then we try to initiate a discussion, ideally based on the questions that have been posted on Slack. Okay. If everyone is happy with that, I would suggest that the speaker of the first paper gives a short summary. I hope that there's a speaker.
Yes. Okay, it's me. Yes.
Okay. Thank you very much. Yeah, then please start.
Okay, just hold on a second. I need to share my screen. Okay, hi, my name is Artem Govorov, and welcome to the discussion on the following paper, which is my joint work with Jenny Tsai and Martin Dyer. So, graph homomorphism originates in the work of Lowas in 1967. Over the years, there's been a great deal of work done on this topic. In particular, there's been an active research area in the complexity of the graph homomorphism function. Dyer and Greenhill proved that for 0-1 symmetric matrices, there is a complexity dichotomy. This was generalized to non-negative symmetric matrices by Boltov and Grove. In the original work by Dyer and Greenhill, the dichotomy further extends to bounded degree graphs. Bounded degree graphs are important for a lot of work in statistical mechanics and approximation algorithms. However, for the Boltov-Grove dichotomy, for non-negative graph homomorphisms, the issue on bounded degree graphs remained open for 15 years. In this paper, we resolved that question. So I invite you to join our discussion.
Okay, thank you very much. And apologies for forgetting to properly introduce yourself.
Oh, my name is
you corrected my mistake.
Yeah, my name is Artem Govorov. Yeah.
So sorry about this. I guess in this online setting, I'm not quite used to it. So I think Daniel and Marx posed a couple of quite interesting questions in Slack, and I'm glad he's also online. Daniel, do you like to?
Yeah, so maybe I repeat my question. So this is a very interesting result, extending it or strengthening it to bounded degree graphs. But there is this technical detail that your theorem says that for every matrix A, there is a degree bound such that the problem is hard already with that degree bound, and of course for different matrices this can be different, and my question is that how essential it is, or what more we can say about this. So for example, do you have interesting examples where for some problem you really know that you really need a large degree bound to make it hard, and for smaller degree bounds the problem is easy?
Okay, let's put it this way. So can I stop sharing my screen, or how it's like?
I guess.
I mean, okay, so yeah. So let's see. So okay, so we have to actually consider, like, just hold on a second. Okay, so we have to consider. We have to consider 4 variations of this problem. First of all, like 0-1 edge weights, non-negative edge weights, real edge weights, and complex edge weights. Okay, so now, of course, if the degree bound is 2, everything is tractable because your input graph is just a disjoint union of loops and path. Then, if okay, for 0-1 case and non-negative case, we conjecture that delta equals 3 is sort of is the universal bound. So it's, for example, if it's, but
really?
It's an open problem. Like, yeah, so it's like if I mean, it has not been resolved. So that's why I mean, if A is not block rank 1, then eval of A is sharply hard, but it's also conjectured that it's sharply hard when restricted to 3-degree bounded graphs. Okay, so for real, I mean, if the weights, if the edge weights are real, then I believe that 3 is not the. I believe again that 3 is not the bound, but there is a finite bound, universal bound. For complex edge weights, this is not the case. So there is no universal bound. So
I mean, so you have a proof for that, or you have an example?
I didn't prove it. It was proved by I'm gonna find just give me a second. It was proved by hold on, just I'm still searching for the link. Yeah, found it. So it was shown by Shia. I mean, excuse me, where can I post
in the chat, I guess, or on Slack.
Okay.
Maybe if you post it on Slack, then it remains even after the session.
So just I'm simply gonna, let's see. Okay, so it was shown by Shia. Yeah, so that there is no sort of universal bound. I mean, it's like it's one of the results in this paper. So there is no universal bound for complex edge weights. So, I mean, yeah. Yeah, so I guess that this answers the first question, right?
Yes.
And
okay.
You have other questions, right?
Yes, but okay. So in light of this, some of them are not that relevant. So as you said, in principle, for real weights, you can prove a universal bound, and this is out of question for complex weights.
Yeah, so but I'm just going to reiterate. So then for 0-1 edge weights, that's unweighted, the unweighted case, and non-negative weights, delta equal 3. I mean, it's a conjecture that delta equals 3. So, but right now it's an open problem.
And so, can you give some explicit nice bound on this degree bound that follows from your proof?
Okay.
In terms of the size of the graph, or maybe some size of the matrix, or something.
Quite easy. So I'm gonna here. I suppose I'm gonna need to share my screen with the slides. So let's see. Okay, let's see. Hold on a second. Yes. So, sorry. So. Okay. So. Okay. So let's see. Let's go to this proof. Okay. Okay, so first, I mean, if you, I mean, we use this lemma. Oh, you don't, sorry.
I still don't see anything.
Yeah, it's a bit stressful for me. Yeah, I've never had a conference online, you know. So just hold on a second.
Yeah, take your time.
Yeah, so I just didn't realize that I wasn't sharing my screen. Yeah. So. Okay. Okay, so yeah, let's oh, it's the wrong one. Yes, this one. So let's get to the proof. Okay, so we use this lemma, I mean, to get this sort of bound. So we use this lemma. So basically, if you have a matrix with no pairwise linearly dependent columns or rows and a positive diagonal matrix, then you can find such a P. I mean, P can be found explicitly, such as this matrix is non-singular. But then we use a sort of gadget. In this gadget, I mean, this we have P thickened, bundles, and but the degree of this gadget is 2P plus 1. So, and this is actually the degree of the graphs that you use for the Sharpie hardness part. So it's 2P plus 1, and P can be obtained explicitly here. But here it's we have A prime, and we have the following matrices instead in place of A and D, and so it can be found explicitly. So, but this bound depends on the matrix A. So
can you bound it in terms of the size of the matrix, or it really depends on the actual values?
It depends on the entries, but it can be computed in polynomial time. Yeah. So you still have to, so for example, divide. So some So for example, you A11 times A22 over A12, A21, something like this. But actually, it's not even So I mean, in terms of this matrix. In terms of this matrix, yeah. So you get this. You can compute P.
Okay, thanks.
So, but P is not bounded universally.
And my final question is there any progress to report on more general cases?
Yeah, we have. Let's see. We have achieved. So a dichotomy for bounded degree graphs for so it's like we claim to have achieved a dichotomy for bounded degree graphs for complex edge weights. Okay, so and I'm gonna post a link to archive. So and here, but in that dichotomy, that proof is way more complicated, and it doesn't follow from this one, from the one discussed. But
yeah, so this is interesting. So in a sense, this is so on the one hand, this is the end of the road, classifying all complex matrices. But on the other hand,
I mean, more advanced ideas were needed to obtain a dichotomy for complex edge weights. So it's like, it's only part of the proof. It's not even, so we use some ideas, but we introduce many more additional techniques, algebraic, primarily, So, and just hold on a second, I'm gonna post a link, so an archive link. So.
Okay, thanks a lot, Daniel and Artyom, but we should perhaps move on now to the second paper, which is Counting Perfect Matchings and the 8-vertex model by Yinxi Chai and Tianyan Liu. Apologies for mispronouncing it. The speaker here.
Hello.
Hello. Welcome. So could you please summarize your paper?
Yeah.
Thank you.
Thanks for the introduction. Let me share my slides. Can you see it now? So so our work counting perfect matchings and the 8-vertex model. This is a joint work also with Jinyi Cai. So we study the 8-vertex model where it was defined on 4 regular graphs, although it was originally defined in statistical physics on the square lattice. There are 8 local configurations. For each one, the in degree of every vertex is even, as well as the out degree. So although there are 8 types of local configurations, we allow 4 possible local weights, A, B, C, D, due to arrow reversal symmetry. So if you flip the arrows on around the vertex, the weight is not changed. And we study the partition function of this problem, where we assume all 4 parameters are non-negative. Here's some notations help you understand the picture. We use this X to denote this red rectangle and everything in it. I use this Y to denote the left oval, and this Z to denote the right oval. And the intersection of Y and Z is not empty, and nor does Y and Z contain each other. So previously, we showed that in this green region, Y intersecting Z, there is an FPRAS, and in this gray region, outside X, it is NP hard to approximate the partition function. And in this paper, we show that outside this Y, the problem is at least as hard as sharp PM. And we also show that inside this right oval Z, the problem can be reduced to counting perfect matching. And the second theorem is achieved using match gates. And our result is tight in the sense that no ABCD outside Z can be implemented using a match gate. It's open for years. What are the constraint functions that can be implemented by non-negatively weighted K-array match gates for K larger than 3? And in this paper, we answer this question for K equal to 4. And they are essentially of those satisfying this kind of form. And that's it. Any questions?
Yeah, are there any questions? I have a quick question. I'm not sure it's a very good one, but on your, if you go back 1 or 2 slides, you had this Venn diagram that summarizes your result. So in this, can you say anything about this white area?
We could say something. We proved some structural lemma, saying that in this whole region, this leftover Y, it also has some property that separates it from the other side of Y, outside Y. For example, if you use constraint function in this left oval and build a larger picture, we call a Fourier construction, then you cannot escape. So using things inside, you cannot reach outside. And this is no wonder because we prove outside is relatively hard.
Okay, thank you. I think there are no questions on Slack, but if anyone has a spontaneous.
So just a quick general question: that do you see this problem setting, this eight-vertex model, as a special case of something, or how does that fit into the framework of other problems?
Oh, so we see this problem. So this is approximate complexity setting. In the exact computational complexity, this is really a special case in the Holland framework. So because you define variables on edges and functions on the vertices.
And so are there other special cases that you would target, or is this somehow special?
Yeah, I would say, so it's special case 6-vertex model. So when the 7 and 8 don't have weight, it's the weighted sum of Eulerian orientations. And in this case, the 6-vertex model has a lot of link to other models, say Potts model, Tut polynomial, and say proper 3 coloring on the square lattice. So it has a lot of links to other models. But for the 8-vertex model, I think on the square lattice is quite expressive. It can express even the square lattice Ising model and dimer model. But yeah, with regard to this, I don't know other things that it's a special case of.
So my question is more like that: would it make sense to look at like degree 6 or degree 8 or other things, or can we expect a paper like that in next year's ICALP, or
yeah, that's a
or this degree 4 is special for some mathematical or physical reason?
Yeah, this degree 4 is mainly interesting because it can be defined on the square lattice. Yeah,
Okay.
it originates in the physics. Yeah.
Okay, thanks.
Thanks.
Okay, thank you. I guess we should move on unless there's a quick question. Doesn't look like. So then we move on to paper 3 or paper C, which is Contraction, a unified perspective of correlation, decay, and zero-freeness of two-spin systems. And this is by Shuai Shao and Eugene Sun. Again, apologies for the terrible pronunciation.
Hi.
Hello?
Hi. Can you see me? So thanks for the introduction. I guess I need to share my screen. Wait a second, please. So thanks for the introduction. So can everybody see my slides?
Yes, it looks all right.
Okay, good. So this is a joint work with Yuxin Sun, who is a PhD student at W Medicine. So let me roughly describe the result of our paper. So two-spin systems is a model in statistical physics to model interactions between neighbors on graphs. And such a two-spin system is specified by
sorry, so we cannot see the slides. So it's still on the first page.
Sorry.
I think that froze while you were enabling the full screen. Maybe if you disable the full screen of the PDF viewer.
Okay. Wait a second.
Yeah.
Okay. Now looks good.
Yeah.
Okay, good. So I guess I will just go it like in this way. So so two-spin systems model interaction between neighbors on graphs, and it's specified by two edge parameters and external field. And so an instance is a graph, and a configuration is a mapping that maps each vertex to a plus spin or minus spin. And for each configuration, we have a weight. And the pattern function is the sum of weights over all configurations. So this is the sum of product computation, and the two-spin system is the basic case of the graph homomorphisms, counting graph homomorphisms, and counting constraint satisfaction problems. And it's known that for two-spin systems on graphs with bounded degree, the property real contraction is the sufficient condition that ensures the existence for correlation decay for certain real parameters. This is also this is usually known as the potential method. And in our paper, we generalize this property to complex parameters, and we show that the complex contraction property is a unified sufficient condition for both the zero-freeness of the pattern function and also for correlation decay. These are the two main methods to devise FP tasks for computing the pattern function of two-spin systems. And also we give some new real parameters that satisfy real contraction. And our main contribution is that we show that if a real parameter satisfies real contraction, then there exists a complex neighborhood of this real parameter, such that for all complex parameters in this neighborhood, it satisfies the complex contraction. So in summary, if we have a real parameter that we can devise an IP task for the pattern function of two-spin systems, then we can generalize it to its complex neighborhood. And our approach is generic, so it does not rely on a particular children potential function. And we hope it to be explored for other models. So thanks. Any questions?
Thank you. Are there any questions? I was wondering, Could you generalize any of your results beyond two-state systems?
The reason why we consider two-spin systems because that by using self-avoiding tree, it can the recursion function can be easily computed, and our approach is based on the property that this this recursion function is analytic. However, for like other models like multi-spin systems, the recursion function is not easily described, and so it might be hard to analyze. So that's a challenge for generalize this model to like multi-spin systems and other models.
Okay, thank you.
Thank you.
Any other questions? We've got a few minutes. Okay, if that's not the case, let's thank the speaker again, and we move on to paper number 4, paper D, which is on graph isomorphisms in quasi-polynomial time parameterized by treewidth. And the speaker is Daniel Wiepking.
Yeah, thank you for the introduction. I hope you can see and hear me. Let me also share my screen. Okay, somehow, no. Okay, for some reason I can't share my screen. Let me try it again. Okay, it seems like it doesn't work, so I will just work without my slides. So basically, I looked at the graph isomorphism problem. So that's the problem I'm working with. And for many restricted graph classes, the graph isomorphism problem is known to be solvable in polynomial time. So for example, if the maximum degree of a graph is bounded, you can solve the problem n to the d, or if the genus of a graph is bounded. Or also if the treewidth of the graph is bounded, you can also solve it in polynomial time. And the degree of this polynomial usually depends linearly on the parameter. And a few years back, there was a breakthrough in the graph isomorphism where Babai gave a quasi-polynomial time algorithm for the problem, that is n to the polylog n, where n is the number of vertices. And my basically main result is that one can generalize this quasi-polynomial time bound if you also consider the treewidth of a graph as an additional parameter. Then you can solve the graph isomorphism problem in n to the polylog t, where t is the treewidth of the graph. So as t is bounded by m, this then clearly generalizes the quasi-polynomial time bound. And yeah, this is my main result, basically.
Okay, thank you very much. By the way, I see that you have a nice whiteboard in the background, so maybe that can be used if you answer some questions.
You see my whiteboard? Okay.
Yeah. Oh, sorry. I hope these are not secret formulas that you intend to publish.
Oh yeah. No, I think most of this is already published. I think it's yeah.
Let's see. There are some questions in Slack by Daniel.
Yes. So I believe you don't know the answer to this, but I still ask. So is there a possibility of having an FPT algorithm parameterized by treewidths where the dependence on the treewidths is quasi-polynomial? So instead of the known 2 to the poly-k algorithms, there's a quasi-polynomial FPT algorithm. So is there a reason why there shouldn't be such an algorithm, or what are your thoughts on this?
Sorry, I think there's some problems.
Yeah, I think I got unmuted, but I think now you can hear me again. So
Yes.
yeah, thanks for the question. In fact, there was the first FBT algorithm of Logstanov and other people who gave FBT algorithm where the dependency on K was like 2 to the K to the 5, and a few years back we extended this to n to the K or something, or if you don't care about logarithmic factors in the exponent, then it's an n to the K algorithm. But yeah, we also, like, our goal was basically to find such an algorithm where the dependency on K is quasi-polynomial, so n to the polylog K, but it was kind of difficult. And I mean, there is this construction of Logstanov and all who showed that you can construct isomorphism invariant tree decompositions, and these decompositions, they already have n to the K back size, and without, I mean, just to construct these decompositions in an isomorphism invariant way, basically that's the only technique we know for this. And I think that will maybe also be very difficult to find tree decompositions of quasi-polynomial size that are invariant under isomorphisms. So if you just work with an approximate decomposition that's not invariant under isomorphism, then most of the techniques cannot be applied to these decompositions when you basically construct or decompose two graphs in structurally different ways. So yeah, you need this isomorphism invariant decomposition, and yeah, that can be quite large. So I think it's a nice question, but I think it's very difficult to find such an algorithm.
And if we look at easier questions like parameterizing, so for example, parameterization by treewidth but on bounded degree graphs, then I mean the structure of bounded degree, bounded treewidth graphs should be much simpler than bounded treewidth graphs. And the easiest question of all would be parameterizing by vertex cover number. So like a quasi-polynomial in the vertex cover number times poly-n algorithm, that would be the easiest quasi-polynomial type FBT algorithm.
I see. Yeah. I think I can't answer this question, but I mean, it might be possible that these kind of algorithm exist. And I think these are nice questions, so that you look on FBT algorithms where the FBT term is quasi-polynomial. I mean, that's very reasonable, and it's also possible and plausible that these algorithms might exist, but I mean, it's difficult to find such algorithms, I think.
Yeah, and so finally, a minor technical question that so in your slides you had this structure with degree at most poly t, and you use the bounded degree algorithm, and then this will be quasi-polynomial. But I just noticed that probably if the structure degree of the structure is quasi-polynomial in T, then this would still work. You are muted, I think.
Yeah, I mean, that's true. If you have quasi-polynomial degree, then that still works. But actually, we could found polynomial bounds there, which is maybe, I think, also kind of interesting. And the polynomial, I think, is also not too large. So that's the reason why we stated it, or why we did this more precise there.
Okay, thanks.
Thank you.
Are there any more questions? Otherwise, I had a minor question or comment. I think there's some results for testing graph isomorphism on graphs with bounded eigenvalue multiplicities. So I'm wondering whether there's any connection between these results and these results for bounded tree width or click width, degree and so on.
I have to admit I never looked much on eigenvalue multiplicity, and I'm not sure. I'm not too much in it to answer it.
Okay, no worries. Oh, sorry, there is one question.
In the chat, right?
Yeah, by Danny Vagnosi, who's asking whether your main results, whether your main generalization of Bye-Bye's results is more group theoretic.
Yeah. I mean, if it's by group theoretic or combinatorial techniques, and that's very nice question, I think. I mean, it's both, but one thing is that you can just combinatorial decompose a graph into these specific parts where you have some nice structure on the graphs, but that result is somehow not the novelty of my paper. That was already done in previous papers, and it's also maybe not that complicated, and you don't need much machinery there. So my paper is mainly it's completely group theoretic techniques then, because the main problem was then to combine all these isomorphisms between these decomposed graphs, and this is done by completely group theoretic methods. And yeah, it's one can say that it's completely group theoretic extension, this paper.
Okay, thank you. We would have time for one more quick question. Okay, otherwise, let's thank Daniel again and the participants of the discussions, and we move on to the fifth paper, B1E, which is on counting homomorphisms in plane exponential time. The speakers are Andrei Bulatov and Amine Dabsetan.
Okay, thanks, Thomas. Okay, I'll try to share the screen. Okay, here we are. Well, we look at the problem of finding the number of homomorphisms from given graph G to, say, graph H. Well, clearly, if you take the brute force approach, well, the maximum amount of time you need is the number of vertices in H to the power of number of vertices in G. But sometimes it, of course, can be done a little quicker. And what we call plane exponential time is, well, what kind of restrictions we have to put on the graph H so that, well, regardless of the size of the graph, well, the number of homomorphisms could be found in time constant to the power of the number of vertices in G. So some such classes are well known. For instance, if H is a clique, this can always be done in 2 to the power of the number of vertices in G. Also, if H is taken from a class of graphs with bounded clique width, well, a similar bound exists. And well, we first of all are trying to generalize this bounded clique width thing. So we come up with a slightly more relaxed measure that also includes some interesting classes of graphs.
Sorry, Andre, we cannot see your screen.
Really?
Sorry.
I can. Okay, wait a sec. Well, but well, can you see it now?
Yes, yeah.
Yeah, okay, good. Sorry. So, well, I'm not showing anything anyway, so that should be fine. Right, so, well, we generalize this measure a little bit, and well, the relaxed version of bounded clique width actually includes things like hypercubes and things like that. So, well, we proved that in this case, well, we can also count homomorphisms in plane exponential time. And also we find a few sort of assorted classes of graphs for which this is also possible, like Nisa graphs and, well, things like that. Okay, that's all from me.
Thanks a lot. I think we're still seeing the first slide, but
because I didn't show anything else.
Oh, sorry, okay.
No.
But it was a nice, concise summary anyway.
Well, I can show something if someone asks something.
Okay, yeah, sorry. I believe Daniel posted some question in Slack again.
Yes. So first, I guess your eventual goal is to have some kind of dichotomy, but how reasonable it is to expect it. So at the end of your talk, you showed there are a lot more happening here than what we understand so far. So is it reasonable to expect a dichotomy in the end?
Well, not from my side. Well, I have no idea what it should be in the end, because so far it's clearly just some kind of occasional graph classes that work this way, and I don't know. I have no idea what is ultimately responsible for plane exponential time. No intuition so far.
Okay, and so when I was looking at this kind of problems, then I noticed that it can be set up in different ways. You can restrict the left-hand side, the right-hand side. You can consider different kind of running times.
Yeah, sure.
So in particular, maybe you can go to that slide that you are considering this running time c to the size of g plus size of h, or number of vertices of g plus number of vertices of h.
Which is this one?
Yes. And maybe if you are considering like f of size of h times c to the size of g. So
well, perhaps. I can comment a little bit on this bound. So it's constant to the power of v of g plus v of h. So normally in both cases of for bounded click widths, in our case, v of h comes from the finding the decomposition or sort of representation of a graph as bounded click width or generalized bounded click width. And v of j is actually the counting algorithm. So yes, in principle, we can play with this v of g, v of h somehow. But I mean, note that if we add even a logarithmic factor, well, this already sort of just brute force, right?
But a logarithmic factor in what?
Yeah, well, if you say, for instance, size of h times log of size of h, right? That's already it's already basically brute force.
So
that's, I mean, you cannot relax the bound too much.
But I mean, the size of each part can be relaxed, and still the main thing is to have a c to the size of g saying.
Yes.
And so with this formation, there are problems like if you add isolated vertices to h, which shouldn't change the complexity, but it makes the problem easier because your running time bound becomes more relaxed.
Well, that's true. So you can add isolated vertices to any side, right? So it doesn't change anything, basically. That's true.
Okay, and so I had one more question that, just as a sanity check. So do you have a quick example of a class of graphs that has a bounded extended click widths but unbounded click widths with the original definition?
Yes, we have. Say, the hypercubes.
Hypercubes. Okay.
Or say, well, if you take a click, subdivide every h with the same graph. Well, that's a graph that has sufficiently large click width. So, or actually, any click with what was that? It's if you take a class of clicks and subdivide every h with just a single vertex. It has unbounded click width, but bounded extended click width.
Okay, thanks. That makes sense.
Okay. Are there any more questions? Doesn't
I have
look.
a question,
Sorry.
if you can hear me.
Yep.
Because you just opened the slide, you find this plane exponential as c to the vertex set times some polylog or some polyfunction. But can you just basically forget this polyfunction and make the c a bit larger? I mean, shouldn't it be just an equivalent definition if you don't care about the polynomial function in the vertex set?
Well, asymptotically, probably yes, but well.
Because I mean, you can just go from c to c squared or something and make this constant.
Yeah, well, on the other hand, yes, you can, but on the other hand, you want to sort of minimize the value of c, right? So polytime factor is okay. Well, you can have any polytime factor, but then you would like to have c as small as possible in a sense. But yeah, well, it doesn't make any much difference, at least. I agree.
Okay. Any more questions?
Yeah, I have a second question. You have or you showed that the complexity of given a graph computing a k expression or this extended k expression for this graph can be solved in this time. How does it compare to the complexity of just computing a k expression? So for the usual click width and not for this.
What was that? Well, I believe it's just the exponent is 2k plus 1 or something like that. So that's it's worse, but not too much worse.
Okay, and did your algorithm, I mean, building on this algorithm for computing?
So, it uses similar ideas in a sense. So in both cases, it's dynamic programming, where you look at induced subgraphs, find the number of homomorphisms from induced subgraphs. Mm-hmm. And the other parameter is the structure of the formula, of the representation or expression, whatever it was.
Yeah, I mean, not computing the homomorphism. I mean, computing the k expression. If you have given
that's very similar thing. Basically the same.
Okay,
thing.
that's also similar.
Very similar.
Okay.
Okay, maybe we can thank Andre and Daniel, the two Daniels, for the discussion and move on to the final paper. We're back on graph isomorphisms, and the presenter is Daniel Nguyen, and he will talk about hypergraph isomorphism for groups with restricted composition factors. So Daniel, we cannot hear you. At least I cannot hear you.
How about now?
Perfect. Thank you.
Okay, then let me share again. Okay, so that's again the slide where I left off. So let me just.
Sorry, we couldn't hear you even at the beginning. So If you could maybe restart. Oh, okay. Well,
yes, I mean, I just started on my first slide, so yeah, there was nothing important there. So basically, the starting point is similar to the work of Daniel Wiebking. So basically, the starting point of my work is this algorithm that we had 2 years ago in a joint work with Martin Grohe and Pascal Schweitzer, where we could show that isomorphism can be tested in n to the polylog d, where d is the maximum degree of the input graph and n denotes the vertices. Yeah, thereby generalizing Babai's algorithm. And yeah, the basic question that this raises is essentially for which other natural graph parameters can we achieve such a running time? And well, we have seen in Daniel Wiebking's talk that we can achieve it for the tree width as a graph parameter. And the main result of this work here is essentially that we can also achieve this for the genus as a graph parameter. So we can achieve n to the polylog g running time. And well, something that I also want to point out is that as a main tool to do this, we have this notion of TCR bounded graphs, T color refinement bounded graphs, where we have this n to the polylog t running time. So essentially where we can alternate performing the color refinement algorithm and splitting color classes of small size. And then trying to find a coloring where every vertex has its own color. Okay, and then on the main technical level, well, we are having to look into group theoretic techniques and generalize the group theoretic techniques of Babai's algorithm. And here the main result is basically where we look at sort of, yeah, isomorphism problem for input objects, where we parameterize essentially by the potential isomorphisms. And the main technical result is that we can solve hypergraph isomorphism for these gamma d groups in this amount of time here, n plus n to the polylog d. Okay, and then I guess I'll just leave on my conclusion slide from the talk and take your questions.
okay, thank you very much. I believe again Daniel has a few questions.
Yes. So first, as your talk highlights, the improvements in graph isomorphism come from improvements in different dimensions, like considering different kind of subgroups in this. In this group theoretic algorithms, or considering different objects, strings or hypergraphs, and also once you have a group theoretic algorithm, then you can try to deploy it for different graph classes, and your paper improves makes improvements in each of these dimensions. But so my question would be, what do you expect next? So in which step, in which way do you see a possibility for a new step, like considering larger class of groups, or considering different objects, or just using known group theoretic algorithms in a new graph theoretic setting?
Probably the latter. I mean, the obvious next question seems to be that I mean, in the meantime, we have also generalized this to graph classes that exclude an arbitrary minor. This is published on arXiv as a preprint, and the obvious next step seems to be topological minors. And I don't think it requires any new insight on the group theoretic techniques, but more like graph theoretic insights for graph classes that exclude topological minors.
And so also on the topic of using the group theoretic technology for larger classes of graphs. So in your talk, you explained that that you show that if a graph excludes a case 3t as a minor, for example, because it's bounded genus, then you can show that it's TCR bounded, and then you can use your algorithm. But do you have a feeling of what else this class of TCR bounded graphs contain beyond the excluding case 3t?
Well, I guess that by now we have realized that it includes quite a lot. So I mean, to start with, it includes bounded degree graphs, because if the graph has bounded degree and you fix a single vertex, then basically you can, I mean, of course, then the neighbors will be individualized, because color refinement in the first step will distinguish the neighbors of the individualized vertex from the rest. And then basically iteratively you can go on. So you have that bounded degree is in there, and basically this notion also appears in excluded minors. So basically what we show is when you have a graph that excludes some fixed graph as a minor, then you have a decomposition into parts that are TCR bounded, and the adhesion width is small between the parts.
I see.
And I believe similar things will be true for excluding topological minors.
I see. Okay. And just about just a question about your proof of showing that if a K3T minor is excluded, then it is TCR bounded. So could you go to slide 16, where you say something about the adjacencies of the color classes?
Yeah, can you see slide 16 now, or?
I see slide 4.
Okay, then I maybe have to stop sharing and switch to the different window manually. Okay, now you should see it.
Yes.
Okay, so then what was your question?
So what can we say about the adjacency between two color classes in a stable coloring?
Well, that has to be a biregular graph.
Biregular graph, and
yes,
and there you have a perfect matching, or
well, you have in particular a perfect matching, but well, I mean the two sides mustn't have the same sides, so. But
yeah,
I mean, actually, that's not even required for the proof, because I mean you need two properties basically, that these gray sets are connected, which you can just get. So for example, if you want to go from this pink set to the pink set, then you can first go to the yellow set, to the blue set, and then via the violet vertex you can go to anything else. Because you're guaranteed that each pink vertex has a yellow neighbor and each yellow vertex has a blue neighbor.
And how do you get your minor? Then can you quickly recall?
Well, the minor is basically you have the three gray sets that form the three vertices on the left side.
And
the green class forms the 8 vertices on the right side.
Oh, I see. Okay, yeah. Okay, so this is all you need. Yes, I see. Okay.
Okay. We would have time for a very, very quick question if there's any, but otherwise, I think we are spot on in terms of time. So yeah, let me thank Daniel Nguyen for the presentation and the discussion, and all participants, all speakers, for this nice session on counting graph homomorphisms, graph isomorphisms. Yeah, that's all I want to say. So thanks a lot. Stay healthy and have a nice day.